Right, so we left off with the anatomy of blood vessels, and we're going to go forward by looking at the physiology. So the first thing we want to discuss is the basic function of blood vessels, which is to provide a pathway for blood. And the way that blood moves through blood vessels is called blood flow. So the movement of blood through vessels, tissues, or organs is measured in volume per time. So usually this is in something like milliliters per second or liters per minute or something like that. Now the blood flow through blood vessels is the same thing as circulation. And the only force that's actually driving this blood flow is contraction of the ventricles. So in order to achieve flow, we're going to use a gradient. I don't know how I never managed to fix that, but blood flows from high pressure to low pressure down a pressure gradient. Okay, so blood is always going to flow from high to low, and we're going to look at how the pressures change in the system to allow that to happen. But it doesn't do it without an opposing force, and the force that opposes flow is resistance. So flow can pertain to any part of the circulatory system, or it can refer to the entire circulatory system. So cardiac output, which we talked about before, is actually the blood flow through the entire circulation in liters per minute usually. Blood pressure is going to define this gradient that we're working with. So pressure is the force exerted against the insides of the blood vessel walls by the blood that's inside of it. So you can kind of think about it like how inflated the balloon is at any given area, where if you had a water balloon or an air balloon, the air or water inside is pushing against these stretchy walls of the balloon, and that determines how much pressure it is. We measure pressure in millimeters of mercury. And the last force that we deal with is resistance. So resistance, as I said, is the opposition or opposing force against flow. And it's really just a measure of the amount of friction that the blood encounters as it moves through the vessels. Most of that friction comes from the interaction between the blood and the walls of the blood vessels. So when we look at flow, then it becomes the ability of this pressure gradient to move blood against a frictional resistance. So blood pressure is going to change throughout the system in order to ensure that there's always a gradient for it to flow down. So the heart has to have the highest blood pressure, and every time it pumps, it's maintaining a really high pressure to move that blood out against resistance. And the force of the heart pumping is sufficient to drive the blood all the way through all the arteries we talked about, through the capillary beds, into the veins, and eventually return it to the heart to get pumped again. So we know that because blood is going to move or flow down its gradient, it's got to be at the highest at the beginning and the lowest at the end, because otherwise we're not going to achieve flow through the entire system. So when we look at the arterial blood pressure, which is by definition going to be fairly high because this is the blood in the vessels leaving the heart, there's going to be two factors that determine the actual pressure. One of them is the compliance of elastic arteries. So remember that compliance is the ability to stretch a bit and then relax again. I might not have talked about that yet, so if I said remember, don't mind me, I'll be covering in a moment. The other one is the volume of blood moving through them. And this is going to be relevant because this is a closed system. The blood always goes around and around and around. So changing the volume will actually change the overall pressure. So because the heart pumps and it has a beat and then it relaxes and refills, it creates this pulsatile pressure within the largest arteries that are receiving that blood as it pumps. The systolic pressure is the peak generated every time the ventricles contract. And in the systemic circulation, so what the left ventricle delivers to the aorta, we see an average of 120 millimeters of mercury. So it's called the systolic pressure because it corresponds to the systole portion of the heart beating. Diastole is the lowest the pressure will go, and this is a reflection of the arteries are stretching every time the heart pumps, and then recoiling and maintaining a fairly constant pressure, but it's still decreasing because the blood is flowing through down its gradient. And so the lowest that it goes is during diastole of the ventricles, because that's when we're refilling the heart and the heart is not pushing any more blood out. So we call it the diastolic pressure. And this is on average 80 millimeters of mercury. There are a couple of other pressures that we can measure. So the pulse pressure is the difference between the systolic and the diastolic. So that means that average pulse pressure, and you do not need to know these numbers, is about 40 millimeters of mercury. And this is what we feel if we touch an artery and we feel our own pulse. So that pulsing is the difference between the pressures in systolic and diastolic. So one of the easiest pulse points is the radial artery. It's on the inside of the wrist, just below the thumb. And if you press the fingers of your other hand against that, you should be able to feel a pulse. Another pressure, and this one is more physiologically relevant, is the mean arterial pressure. So a mean is an average, and this is the average pressure in the arteries. So it's ultimately the pressure driving blood flow, because the systolic and the diastolic, they're changing, but over time we have this average amount of pressure. So the cardiac cycle is not even. Systole takes about 30% of a total cycle, and diastole takes about 2/3. And so that means that the heart is in the systolic pressure about 1/3 of the time, and diastolic pressure about 2/3 of the time. So there's a couple of different ways we can represent that mathematically. You guys don't need to know that. I'm just showing you how we calculate it. Because usually when we think about averages, we just add up the numbers and divide by the total number, but we can't do that because the period of time that we're in each pressure is different. Yeah, so this is usually somewhere in the like 90 to 100. It does depend because these pressures do change. So we can look at this on a graph and see how this changes throughout the whole system. So when you get your blood pressure measured, you're typically getting it measured around here. And so you're getting the same pressures that we see coming right out of the heart. So when somebody measures your blood pressure, they're cutting off all the blood flow through that artery, and it takes more pressure than is inside those blood vessels to occlude it. So that's how you get your systolic pressure, is you know how much pressure you're exerting to stop blood flow. And then when we get the pressure below what the minimum pressure is in there, then we're going to get free flow again, and that's what gives us our second number. So if you've ever gotten your blood pressure measured and they tell you that it's 120/80 or something like that, what that means is your systolic and your diastolic. Now you can see that this is showing you the mean pressure as well, and that once we get past these elastic arteries, we see a drop in the blood pressure. And again, this makes sense because we have to move the blood down its pressure gradient. So the pressure has to steadily drop in order for blood to continue to flow through. At around the level of the smallest arterioles and the beginnings of the capillary beds, we lose the pulsatile nature of the pressures and it becomes a steady state. And that's because at that point, that change is no longer registering. And so now it really is just a constant pressure that continues to drop, as you can see. This is just in your book, some of the arteries that are easier to feel. You guys don't need to know them, just feels like we need a visual for pulses. Yeah, we're just gonna skip this. Don't really need to know it. All right, so then once we get over to the venous side, now we have that constant pressure. So there's no pulse. So you cannot feel a pulse in your veins, okay, only in your arteries. And the pressures are low and the gradient is quite low as well. So from the venules to the vena cava, which are the last vessels before the heart, there's only a difference of 15 millimeters of mercury driving the blood flow. So the pressure is almost zero as it's emptying back into the heart. So that means that it could be easy to stop that flow by altering the pressures so that you're removing that gradient. So there are additional mechanisms that the veins have to ensure blood is actually returning to the heart, not only on a constant level, but at the same rate that it's exiting. It's exiting at really high pressure, it's easy to get it out. We need to make sure that it's coming back the same way all the time. So we have venous return mechanisms which aid that pressure gradient in achieving blood flow back to the heart. So the muscular pump is what we call it when veins run through skeletal muscle. So when your skeletal muscles are contracting, they squeeze those vessels and that pushes the blood through, and then they relax and the vessel kind of refills and the muscle squeezes and it pushes through. So it's literally pumping the blood back to your heart. The respiratory pump kind of works in a similar way. So blood vessels within the thoracic cavity can have their flow enhanced or inhibited by the pressure changes within the thorax when you're breathing. We'll talk more about those pressure changes next week when we get to the respiratory system. But basically, breathing in and of itself can kind of aid in venous return. Now, the muscular pump especially only works because of the valves that I mentioned last time that are in these veins. So that way we can't get backflow when the skeletal muscle contracts, we're only going to get forward flow. The veins block it. The third mechanism is called sympathetic venoconstriction. So this refers to the sympathetic nervous system, so our fight or flight reflexes, and then venoconstriction literally just means veins squeezing. So this is where the sympathetic nervous system activates the smooth muscle inside of the veins and decreases the diameter. And this reduces the amount of blood that can fit in those veins because now those veins are literally smaller. And so the only place for it to go is into the heart and out to the rest of the circulatory system. And so this is how we can change how much blood is staying in the veins, because as I do believe I did mention, the veins do act as a reservoir. So when we're at rest, we don't necessarily need all of our blood flowing too much through, and so they can kind of hang out in the veins to a certain extent. And then if we do need them, usually because we've increased our physical activity, we can venoconstrict, and that changes the proportion of blood in the veins versus the arteries and the capillaries. So this is a diagram of the skeletal muscle pump. So you can see we have a vein here running in between some muscles, and we've got valves. And when the skeletal muscle squeezes, it pushes the blood the only direction it can go because the other valve is blocking backflow. And once it gets past this next valve, then, you know, we've made at least some progress. So because of this, though, we can definitely get blood pooling, especially in our lower extremities because of gravity. And this is one of the reasons why it is important to move on a fairly regular basis, especially if you have a job that makes you sit a lot of the time, because blood pooling all the time can have negative consequences. It's really hard to find a good picture of the respiratory pump. This is as close as I could find. But basically, when you breathe, there are times when the pressure inside of your chest is less than the pressure in the surrounding atmosphere, and so that's going to help push the blood. So we'll talk again more about those pressure changes when we get to the next system. So basically, the various factors that can influence blood flow and therefore blood pressure are going to be anything that interferes with the pressure gradient. So if you increase the pressure gradient and you make there be a bigger difference between your systolic and your diastolic pressure, then you'll increase flow. And if you decrease the gradient, so you bring your systolic and diastolic pressures closer together, or you decrease your venous pressures, or sorry, I'm thinking about this backwards. If you increase your venous pressures, then you can impede flow and cause problems. So there's a lot of different things that can affect this. We'll touch on each one. We won't go into a ton of detail because we don't have time, but hopefully you'll understand the key concepts. So cardiac output is definitely something that will affect blood pressure and blood flow. We talked about cardiac output already though. So cardiac output is literally blood flow through the whole circulatory system, and it's going to be determined by heart rate and stroke volume. So anything that increases cardiac output increases blood flow, and so anything that increases heart rate or stroke volume or both. And then vice versa, anything that decreases cardiac output will decrease blood flow. So we're not going to touch on them again, we're just seeing that this applies to the rest of the circulatory system and not just the heart. Compliance is the other big factor here. So compliance is just the ability of a compartment to expand to accommodate increased content. So we've been touching on this a little bit. It's a little bit hard to explain. It's just kind of like how well something can stretch, essentially. For example, a metal pipe has no compliance because you can't make metal stretch. But a balloon has a ton. And blood vessels fall somewhere in between that. You don't really want them to be on those extremes. We want enough compliance to increase blood flow without increasing resistance, but we also don't want to significantly increase blood pressure either. Now, veins are more compliant. They're stretchier and able to accommodate more volume changes. That's why they're good at being blood reservoirs. Arteries have the right amount of compliance to maintain that pressure gradient that we saw on the chart. So they're stiffer than veins, but not so stiff to cause problems as long as they're healthy. Diseased arteries, so typically ones that it's called atherosclerosis, where the walls of the arteries harden a little bit and they become stiffer, this decreases the compliance. And because they're no longer able to expand to accommodate changes in blood flow or volume, we get more resistance, and that results in an increase in blood pressure. And so now, in order to keep flowing the blood through, we need to increase the blood pressure upstream so that we still have a gradient to work with. So now the heart has to work harder in order to pump the same amount of blood. And that's one of the ways that we cycle into this deterioration of the circulatory system that will ultimately result in heart failure, making your heart work harder when it shouldn't have to. So actual sources of resistance are anything that impedes blood flow. And the major thing that's going to impede blood flow, again, is the interaction between the blood and the walls of the blood vessels, because this is all about friction. So the three main factors, which we will touch on, they all have their own slides, are blood viscosity, blood vessel length, and blood vessel diameter. Blood viscosity is a fairly constant trait that just refers to how thick your blood is. So you can kind of think about it like as a stickiness too. It's defined as the internal resistance of a fluid. And it's basically just a function of the proportion of your blood that is red blood cells and proteins. So this is an example of, I think that's honey. That's a quite viscous fluid, so it's quite thick. Water is, of course, not viscous at all, flows very easily and fast. Blood is closer to this, flows pretty well, but is certainly more viscous than water. But we don't worry about this too much because it doesn't change very rapidly. It can in certain cases, but for the most part, it's not a highly changing thing. Neither is total blood vessel length. So total blood vessel length is literally just how many blood vessels you have in your whole body. Basically, the bigger you are, the more you tend to have. And so you get more resistance when you have more blood vessels because that's more blood vessel wall to have friction with the blood. But it's pretty constant, so we don't worry about it when we look at, the kinds of things that can be changed as far as actually influencing flow on like a daily basis. So the only one that can really be changed rapidly is blood vessel diameter. So diameter is just how wide across it is, right? So if we look at this on cross section, that's the diameter. And the thing is that the smaller diameter blood vessels have more resistance than the larger diameter ones. And that's because a larger proportion of the blood flowing through is interacting with the wall. So when you have a small one, even though the walls are smaller too, all the blood out here has friction and then the stuff in here doesn't. If you have a nice big one, then sure, this layer out here has friction, but all the blood inside does not. So smaller diameter vessels, which mostly we see this with arterioles, that's the major vessel where we're going to see this be relevant, are going to have more resistance. Now the thing is, we can change the diameter of these blood vessels because of the smooth muscle in the tunica media. When we decrease the diameter, we do that via vasoconstriction, and when we increase it, we do it with vasodilation. So vasoconstriction is when we're making the smooth muscle contract and shrink it down. Vasodilation is when we make the smooth muscle relax. Vascular tone refers to how much of a contraction the smooth muscle has at any given time. Typically, it's somewhere in between. So we don't usually have no vascular tone, but we also almost never have full vascular tone. So the smooth muscle should be working a little bit, but not a ton, and that's how we're maintaining this blood pressure. So you can have pretty big changes in the resistance with fairly small changes in diameter because it does have such a big impact on the proportion of blood that is experiencing friction as it flows through these blood vessels. This is just some charts kind of showing how this stuff works. So this first one, upper left, is showing you blood vessel diameters. And of course, your bigger arteries and your bigger veins have quite large diameters. And, your smallest ones are, of course, your capillaries. Now, the interesting thing, though, is that we have a ton of capillaries and arterioles and venules, and we don't have that many of the big arteries and veins. So when you add all of them up, the total area that you can hold blood in them is much, much higher in these teeny tiny guys. This one's just showing you that the blood pressure steadily decreases as blood flows down its constant pressure gradient. And then this one is showing you how fast the blood is flowing. So it's slowing down as it moves through the arteries, moves very, very slowly through the capillaries, and then it slowly speeds up again as it gets channeled into these larger and larger veins. And I'll touch on that a little bit more later. All right, so what we've been talking about is essentially factors that affect circulation. And so because blood flow is based on the blood pressure gradient minus however much friction we have, so peripheral resistance is what we call it, we know that these things have an effect. So flow is going to be equal to the difference in pressure between 2 points. And the bigger the difference, the higher the flow. And flow is also inversely proportional to the peripheral resistance. So the more resistance there is, the lower the flow. Which you can kind of think about as like when you get more resistance, you tend to increase the pressures down the line and you're interfering with the pressure gradient. I don't know why I can't stop saying concentration. So yeah, so that's kind of how this works. We just kind of look at, you know, what promotes flow and what blocks flow. The other big concept on the blood vessel side of the circulatory system is what happens at these capillary beds. Because all of this stuff is all well and good, but if you're not actually exchanging things at the capillary beds, then this whole circulatory system is worthless. So capillary exchange is referring to blood exchanging substances with body tissues. This can only happen at the capillaries because they're the only ones whose blood or whose vessel walls are thin enough to allow it to occur. Now, capillaries have really small diameters, and what we expect as we're shrinking the diameter of something is to have an increase in flow. That's not actually what happens though, because there are more capillaries in the body than any other type of vessel. And so blood is actually flowing very slowly through them, as we saw on that chart that I showed you. That's because the velocity or speed of blood flow is inversely related to the total cross-sectional area of blood vessels. So the total cross-sectional chart, remember, looked like this, where we have a ton of room in all of the capillaries when you add them all together. And so that means that we can have the blood flowing really slowly. This is kind of like the difference between a river that's running through like a really deep riverbed and it's going really fast and it's like, oh man, that would be a good one to like ride the rapids on. I've never done that, but I understand that's how it works. And that's as compared to like when you hit part of the river where it's really, really wide, but it's like so shallow that you can just like walk through it and not get your pants wet. The water moves really slowly there because it's all spread out and it has lots and lots of room. So the capillaries are like the really wide portion of the river. It's just that it happens to be all divided up into different channels. So as we're slowly moving the blood through the capillaries, we have a chance to move substances both into the tissues and out of the tissues, or into the capillaries and out, whichever, doesn't matter. And the majority of how stuff moves is called bulk flow, which is where we're forcing fluid out of the capillaries through those intercellular clefts that we mentioned when we covered the capillary anatomy. It usually happens at the arterial end of the capillary bed because the pressure is higher there. And the cool thing is that as the capillary flows, it loses pressure because it's moving fluid out of it. And by the end of it, fluid starts coming back in because the pressure in the tissue bed is higher than it is in the blood. And this is important because that means that even though we've exchanged materials, mostly we're leaving nutrients and oxygen with the tissue beds, and we've picked up carbon dioxide and metabolic waste products, we're keeping most of the volume of the blood. We're not losing it to the tissues. So the ways that the different substances can move through basically follow the diffusion across plasma membrane rules that we've talked about before. So the nonpolar substances can diffuse through the plasma membrane. So this, for example, is how oxygen and carbon dioxide move. Small water-soluble substances can either use those clefts between the capillaries or fenestrations in the holier types of capillaries. And then larger molecules have to be transported across the cell walls, across the cells of the blood vessel wall. So the capillaries, remember, have those endothelial cells, and they actually have to grab these larger molecules and move them through in little vesicles, which are little membrane organelles, if they want to actually deliver them out. So most stuff moves through those clefts with the water of the blood, and then it just passively moves down its concentration gradients. So we're mostly dealing with diffusion here. And the nice thing is the concentration gradients favor the directions that we want all this stuff to go. So the tissue cells are using oxygen and nutrients, so they're keeping their levels really low, and so the gradients always favor moving oxygen and nutrients into the tissues. And because they're always making carbon dioxide and metabolic waste products as they use the oxygen and nutrients, this favors the movement of carbon dioxide and waste products into the blood because they're at a higher concentrations in the tissue. So then everybody's just passively moving down their gradients, and we're achieving the exchange that we want. Okay, so that is capillary exchange in a nutshell, and I kind of wish I'd left a picture in, but I didn't. There's a lot more to it than that when we get into the details, but again, we don't have time for that. All right, so mostly this is about diffusion. So the last thing we want to tackle then is, and we did not talk about that, oh boy, is how these things are regulated. So we talked about blood flow and blood pressure. We just talked about capillary exchange a little bit. So how does this actually get regulated? Well, there's of course a variety of methods, and it works very similarly to cardiac output. So we can break it down into 3 different types of mechanisms or regulatory to maintain blood flow, blood pressure, and tissue perfusion. So we have nervous system input, endocrine system input, and then autoregulatory mechanisms, which refer to local things that the blood vessels can do to regulate themselves, or that the tissues do. So tissue perfusion refers to how much blood is flowing through the body tissues. And we always want enough blood flowing through that it's effectively delivering nutrients and removing wastes, effectively exchanging gases when we're in the lungs. We want to pick up more oxygen and get rid of carbon dioxide. We want enough blood flowing through our digestive system when we've eaten to absorb all of our nutrients. And we want our kidneys to get enough blood filtering through them to form enough urine to get rid of waste products. So we want that flow to match the needs of each tissue and each organ, and the needs are going to change. So like your digestive system doesn't need as much blood flow when it's not actively digesting a meal. You probably don't need quite as much blood flowing through your lungs when you're resting versus when you're exercising. Same with your skeletal muscles, stuff like that. So the first step in making sure that tissue perfusion is adequate is with this autoregulation. It's also called intrinsic controls because it refers to the tissues themselves regulating blood flow through them to match the tissue perfusion with the tissue's needs. Now, that's not always going to be sufficient. So we can't always let all the tissues just ask for what they need and receive it. And that's because there's just not enough blood in the circulatory system to fully perfuse all tissues if they have high requirements all at the same time. This could massively tank your blood pressure and cause everybody to lose out on appropriate perfusion. So the extrinsic perfusion controls are how the nervous system and the endocrine system make sure that the critical regions of your body always get enough blood flow, even if the less critical regions are demanding more blood than you have to spare. So the autoregulation, that does not belong there, pretty sure. So the autoregulation, what we already said, we already covered. Don't worry about that, it doesn't add anything. So the blood flow to special areas is about how we have these critical parts of the body that just don't get to be deprived, like ever, because the consequences would be too high. And basically that's the brain, the heart, and the kidneys, although the kidneys do get screwed over if absolutely necessary. So the brain and the heart are the most important, because if you deprive them of blood flow, then you're probably going to die, or at least suffer some pretty intense consequences. And, you know, bad things happen if your kidneys don't get blood for long enough, but they will get cut off for short periods of time in the interest of immediate survival. So they are special because they don't follow the normal rules of autoregulation, which says that, you know, the extrinsic controls can override it because they are the critical areas that need the priority flow. Now, if we're constantly having an issue where a tissue needs more blood flow and it's not receiving it, the tissues are actually able to increase the number of blood vessels that they have. So this is a long-term auto-regulation. It's a long-term adjustment made for constant lack of nutrients. Angiogenesis is what we call it. It's new blood vessel growth, as well as enlargement of existing blood vessels. So if we have tissues that are just constantly getting deprived, then we're going to have this happen. One of the common locations for this is the vessels around the heart, so the coronary blood vessels. We also see this in people who have adapted to living at high altitudes because they're chronically hypoxemic. So basically, because there's less oxygen in the atmosphere, they don't have as much oxygen to deliver to their tissues, and they will actually make more blood vessels in response. That's not going to help that much, but it might help a little bit if they're happening in the lungs. When it comes to regulating blood pressure, this is about regulating the things we've already talked about. So we know that cardiac output is going to have a major effect on blood pressure, as well as peripheral resistance. The third factor here is blood volume. So blood volume is going to be a major player too, because the amount of blood in the total system is going to dictate how much is available to pass around, as well as the body's ability to change blood pressure through the heart. So remember that blood pressure changes are going to be quite dependent on cardiac output. They're also directly proportional to resistance. So that's a little bit different from flow, because remember that with flow, it's the difference between pressures from one point to another, and resistance is inversely proportional, where when resistance goes up, flow goes down. But with blood pressure, what this means is that anything that increases cardiac output will increase blood pressure, but it also means that anything increasing resistance will also increase blood pressure. So just like perfusion, we have short-term controls and long-term controls. We don't have like a Auto-regulation here because we're dealing with like the whole system. But for the short-term controls, it's about nervous system and endocrine system. And then long-term regulation all relies on the kidneys. So neural regulation is all about monitoring your mean arterial pressure and adjusting the diameter of your blood vessels to maintain an appropriate pressure level. It can also alter perfusion. So it can alter the distribution of blood in response to the demands of specific organs. And it does this by vasoconstricting at key junctions and potentially cutting off capillary beds with those meta-arterioles. Give me 1 second. Sorry, where was I? So, yeah, so this occurs mostly in the same places that all of this stuff occurs, which is going to be the hypothalamus and the brainstem. So we have cardiac centers and vasomotor centers. So vasomotor just refers to how much your smooth muscle in these blood vessels is working. So vasomotor tone, which is what we typically have, is that most arterioles are moderately constricted most of the time. And that's because at rest, we don't need, most of our tissues don't need all of our blood, which is how we end up with a lot of it being stored in those venous reservoirs. I don't know why I'm harping on that. It just keeps coming up in my brain. Okay, so an example of this neural regulation is baroreceptor reflexes. So baroreceptors monitor blood pressure by monitoring the amount of stretch in arteries. And what we see is when blood pressure increases, these stretch receptors see more stretch, and that's going to stimulate cardioinhibitory centers in the brainstem, and that's going to result in vasodilation, as well as a decrease in cardiac output. Both of these things are going to decrease blood pressure, and that'll decrease stretch and turn off this reflex. The opposite will happen too, so a decrease in blood pressure will stimulate that we have cardioacceleratory centers too, and that'll result in vasoconstriction and an increase in cardiac output, which will increase blood pressure. So here, this is in diagrammatic form. So baroreceptors are in the major blood vessels. They're in the aorta and the carotid arteries, which are the ones that deliver blood to your brain. So they are monitoring this. When they detect a change in blood pressure, they're going to respond accordingly. Now, higher brain centers can also have an effect. So this is where we get the hypothalamus influencing what's happening in the brainstem. So medullary centers are brainstem. And so, for example, because the hypothalamus has a strong role in autonomic control, they can, it'll control blood pressure during your sympathetic nervous system reflexes, as well as redistribute blood flow during exercise and thermal regulation. So during exercise, we're of course going to increase it to skeletal muscle and the heart and the lungs. And with thermal regulation, it depends on whether you're hot or cold, but we're going to change the amount of blood flow to the skin. So we have these nice flow charts that show you how this works. You can see increased blood pressure, is going to have these effects, and decreased are going to have these effects. pretty much what I said, but in a nice flow chart. When we look at endocrine control, we're looking at a variety of different hormones that can regulate blood pressure. Some of them do this by changing peripheral resistance. So that's mostly going to be, again, changing blood vessel diameter. And then some of them work in a more long-term fashion by changing blood volume. That takes longer, so it's a long-term regulation. Local tissues produce local hormones called paracrines that do help match blood flow to their needs. Basically, waste products increase blood flow so that they're not, having issues. Oh, sorry. These are the major hormones we're going to look at very briefly, and we'll look at some of them in more detail when we get to other systems too. So epinephrine and norepinephrine, of course, are the endocrine branch of the sympathetic nervous system. So they're going to have the same effects. So they're going to increase cardiac output, and they're also going to cause a generalized vasoconstriction. This is going to do a pretty good job of increasing your blood pressure quite fast. We do have other hormones that can do this too, though. So angiotensin II is a hormone that is already circulating in your blood, and it gets activated as needed. It also causes vasoconstriction, and it activates two other hormones. So it activates aldosterone, which hopefully you remember causes you to retain more sodium and therefore water, and that increases blood volume. And also antidiuretic hormone, which we talked about as well. So that's coming from the pituitary gland, and that causes the kidneys to retain more water. So both of these are going to pretty effectively increase blood volume, and that leads to an increase in blood pressure. This guy does cause vasoconstriction, but only at very high levels that you're not likely to make in real life. So mostly this is about increasing blood volume. This guy is the only one that worries when your pressures are too high that you might need your blood volume to decrease. So this one works the opposite of antidiuretic hormone and aldosterone, and it actually makes you urinate out more salt and water. So this one's going to decrease your blood pressure if it's too high. So I said that the kidneys are in charge of long-term regulation, in part because they're the ones doing all the work when some of those hormones are responding about blood volume changes. But they can do it in a couple of different ways as well. So there are direct renal mechanisms whereby the kidneys themselves are affected by changes in blood pressure and reflexively act to bring it all back to homeostasis. So basically, when we have increases in blood volume and pressure, we increase the amount of fluid being filtered out into the kidneys as they make urine. The kidneys can't retain or reclaim all of that fluid, and so you lose some of it and you urinate more out. So when you have a lot of blood volume, you're automatically going to make more urine, okay? And this will decrease your blood volume, and blood pressure will then decrease as well. So this is a direct mechanism whereby it's simply a consequence of the way that the kidneys filter your blood and make urine. We see the opposite occurring if our blood pressure and volume is too low, because now we're slowing down the amount of filtration in the kidneys, and the kidneys reabsorb quite a lot more fluid, and so you're making very concentrated urine. So that helps maintain blood volume. You, of course, can't increase blood volume without ingesting more, but it does help slow a drop in blood pressure. So again, just a natural consequence of the way that the kidneys make urine, and how that works we'll talk about when we get to the urinary system. Now, indirect mechanisms are how the kidneys play a role in these hormonal responses. So when we look at this angiotensin that I mentioned before, we see that there's a little bit more to it than that. So angiotensin is involved in a chain reaction that actually starts in the kidneys. So we call it the renin-angiotensin-aldosterone mechanism, or RAS for short. And renin is released from the kidneys when blood pressure, blood volume decrease. So it's actually triggering the activation of angiotensin in the blood, which then, as I mentioned, stimulates aldosterone and antidiuretic hormone secretion. So we're retaining sodium and we're retaining water. It also makes us feel thirsty so that we drink more. And as I mentioned earlier, it causes vasoconstriction, and that's going to increase peripheral resistance and increase blood pressure as well. So this is a really powerful combined mechanism that has pretty fast and slightly long-term effects on maintaining blood pressure. And it actually starts in the kidneys because renin is an enzyme secreted by the kidneys that activates the angiotensin. So this is kind of a summary of that. So short term is going to be the direct mechanisms, which they don't have on here, as well as sympathetic activation, this is all of them. So the short-term stuff is all about sympathetic nervous system. This is, of course, for a decrease in blood pressure. Long-term is mostly through the kidneys to actually activate the hormonal responses. Although technically, this usually doesn't occur unless you've actually lost red blood cells from bleeding. If you did actually lose blood and had to replace blood total and not just the watery portion, you would make more red blood cells as well by release of the hormone that stimulates it, erythropoietin, which we talked about last time. This is kind of the overflow summary of the neural and endocrine mechanisms. So these flow charts are really nice to sort of study the effects. They don't really go into more detail than you need to know either, so they're kind of nice, and they make a good way to address the material. So I would look at these and go through them with the slides and see, kind of plug in everything that you actually need to know from them. All right, so that is the rest of the blood vessel stuff, which finishes up the circulatory system. Please let me know if you have any questions about this stuff. There will be a worksheet going up as a practice quiz, and we will start with respiratory system next week. So see you soon, and hope y'all have a good weekend.